All right, so tonight I'm going to be talking to you guys about the subject of my master's thesis and the subject of the poster that I got the Chandra Award for. And if you read the program for tonight, you know I'm going to be talking about dark cloud encounters. And this is an idea that was my advisor's, actually. I wish I could claim credit for it, but it was all his. It's actually not a new idea, though. If you ever watched the Twilight Zone, there was a reboot that happened in about like 10 years ago, and there was an episode that concerned a dark cloud that passed over the solar system and blocked out the sun and life on Earth. You know, it was questionable what was going to happen. And there was a science fiction book written by an actual astronomer, Fred Hoyle, about an intelligent dark cloud that was moving through space and overtook the sun and threatened life on Earth yet again. That's the so it's not a totally new idea. And the first one to formally suggest the idea of cosmic seasons is Harlow Shapley, and he should look familiar if you've been in the lobby of the CFA here. He was a director of the CFA for about 30 years, starting in 1920. And he wrote this paper, A Note on Possible Factors in Changes of Geologic Climate, where he talked about as the sun moves in its orbit around the center of the galaxy, it's going to encounter different environments. And what would that mean for life on Earth? All right, so that's the cloud encounter half of it, and I'll go into more detail with it later. But before we move on, I have to introduce what's happening in the background of all of my slides. What we're looking at here is a zoom in on a star in the Orion Nebula area. And the bright part of the Orion Nebula is off camera right here, and it's blowing this interstellar medium wind over this star. And you should be able to see there's like an obstacle, or there's an arc around that star. And what that is from is this wind that's blowing off of a star called a stellar wind. The sun has one too. We'll get to that later. But this wind that's moving off the star creates a bubble that is like an obstacle. You can kind of think of it as like a boulder in the middle of a stream. So the water is moving towards and around the boulder because it can't really go through the boulder. So that's a little preview. We're going to come back to that, I promise. But now I'm going to walk you through the idea of encountering these clouds. So like I said, well, this is a map of the Milky Way. Did I do that? Is there a way we can make it dark again? Okay, cool. Thank you. No, I had that power. All right, so this is I'm just going to ignore it. This is a drawing of the Milky Way from above. We're looking down. It's the center of the Milky Way. This is the sun right there. And the idea is, in its galactic year, as the sun goes around the center of the galaxy, this thing is not moving as a solid disk, like a record or a CD, right? Everything just kind of got its own motion. It's mostly moving together, but there's wiggle room, and so things kind of interact with other things. So as the sun goes around the center of the galaxy, it's going to run into different types of interstellar medium, and that's astronomer speak for clouds of gas and dust between stars. But I'm going to be saying ISM a lot, so I want you guys to remember what I'm talking about. I mean, clouds of gas and dust between stars. And this is a bunch of pictures of them right here, and you can see that they never look the same. Some parts look thicker than others. This one in the middle is really thick. You can't see through it. Parts of this one you can see through, other parts you can't. This is the Orion Nebula again right here. It's very pretty. But one characteristic about ISM that I'm going to talk about repeatedly, and I'm going to want you guys to have a good feel for it, is the density of type of ISM, or the interstellar medium I'm talking about. So there's some ISM that's so thin that if you make a little box that's an inch on a side, you make a little cube, and you scoop some ISM up, sometimes you're only going to get 8 particles. And believe it or not, there's 8 little dots in there, and those are supposed to represent really thin interstellar medium. There's some types of ISM that if you take that inch little box again and scoop it up, you're going to get 200,000 little particles. And to compare that to to how dense our air that we're breathing right now is, if you took an inch cube box of the air that we're breathing, it would just be pure. black. So even the densest ISM that we see in space is really not that dense compared to the air that we're breathing. So density, when I talk about density of interstellar medium, think of that little inch box and how many particles are in it. Okay? So now I'm going to take you on a tour. I'm going to go back to the slide a few times. Take you on a tour of the sun's local neighborhood. So we're going to zoom in on region around the sun. So what we've done here is we've taken that map of the Milky Way and tilted it up at the top, and now we're zooming in on a box that's about 1,500 or 1,600 light years on a side. And this is called the local bubble. It's this region of space that's filled with ISM that isn't very dense at all. So if you took your little box, you wouldn't get a lot of particles in that. And that's all this white area right here. And the sun happens to be very close to the middle of the inside of that bubble. The local bubble is ringed by thicker and darker clouds on the outside, and that's what these darker contours are. And those, if you took your little inch box and scooped out some particles, you'd find a lot more in those. So those are higher density clouds. Okay, now we're going to zoom in even more. We're going to go right to the edge of the arrow and look at the region surrounding the sun. This is 1,600 light years on a side. Now we're going to go to about 30 light years on a side. This is the local interstellar cloud. I like to call it the purple potato. But what this is, it's one of those clouds. It's not really a dark, scary cloud. That's I was kind of talking about in my title slide. It's not very dense. It's a little denser than the local bubble, but it's our little purple potato. We're inside of it. This is the sun right here, and we actually happen to be pretty close to the edge of the local interstellar cloud, and we're actually moving out of it. The purple potato is going one way, and we're going the other. So stay tuned for changes, I guess. It'll be a few thousand years, don't worry. Now we're going to zoom in even more to the area right around the sun. Okay, there's a lot going on in this slide, but we're going to go through it. Remember that my background slide? Remember that arc that we saw? That has a name, and that's called a bow shock. You see it up there. That's that first obstacle for the interstellar wind as it's moving over a star. It makes that ripple around the front edge of it. On the inside, on the innermost region surrounding the sun, we have this egg-shaped region, which is called the inner heliosphere, and it has this boundary called the termination shock, and we're going to talk about that a lot. We're going to go over all these boundaries. So you can see the orbits of the outermost planets surrounding the sun. The tilted one is Pluto right there, and all throughout this egg, that stellar wind, or that solar wind that I was talking about, is blowing off the sun, and that's made of charged particles and light and other things coming off of the sun. And it's moving super fast throughout the inside of this egg, and then it gets to the edge, and it slows down. And that's what's happening here, too, to the ISM. The ISM is moving really, really fast until it hits this obstacle, and then it slows down. There's a third boundary between the two. So you have the bow shock on the outside, the termination shock on the inside, and then the heliopause is the one in the middle. And just to outline those three boundaries as we move on, there's two. This is the termination shock in yellow, the bow shock in the pink, and then the heliopause in orange. So those are those three boundaries. And here's a movie of the heliosphere. Is it going? Okay, so there's the sun, innermost planets, rest of the planets. We're zooming out. The circle is the termination shock. This region surrounded or encompassing, or the blue region, that's the heliopause. And the bow shock is, again, out here. That's that first obstacle. So this is the solar wind shooting off of the sun. That's what makes up everything that's inside the heliopause. The inside of those two first boundaries is all from the sun. And on the outside is interstellar medium. And you see they don't really mix. The interstellar medium doesn't really come inside of the heliopause, and the solar wind doesn't go outside of the heliopause. Okay? And just like we saw in our warm-up thing, we've actually been to those boundaries, or we're getting to the first one. It's a little unsure which boundaries we're going through. That's what scientists are arguing about a little bit. So these are the Voyager spacecraft. They were launched in the 70s, and they've been moving throughout our solar system for the past 30-so years. And they're nearing that termination shock, or they're crossing it right now. And these were some of the headlines that we saw today. Voyager 1 space probe reaches outer fringe of solar system. And then I think this was the one that we saw earlier. Voyager system exit debated. Humanity leaves solar system, or maybe not. And I was wondering what was happening. And then I realized Christine actually sent me this headline yesterday. And when I looked at it yesterday, it had a different title. And the title was great. I loved it because it was like Elvis had left the building. It was Voyager 1 has left the solar system. I was like, that's awesome. And I wish I would have gotten a screen cap of it, but I didn't do that until today. So scientists complained because they're like, wait, it hasn't totally left the heliosphere. So then they had to go and issue an apology and say this is more it. So it's on its way. It's crossing the boundaries. It'll be out there soon. And this is how they know that it's, this is how they know it's entering something different. Okay, so these pink particles, you can think of those as the solar wind particles. And the Voyager spacecraft for the last 30-something years has been detecting just particles from the sun. And then all of a sudden, something changes. And it's going to happen right now. So it starts noticing these blue particles coming in, and they're not actually blue. They just they've been able to determine that they're different types of particles, and they're moving in different directions. So they know something is happening right now, and this they think is probably either the termination shock or nearing the heliopause, and they'll know that the sun or the Voyager spacecraft has left the solar system entirely when it sees no more pink particles, because the heliosphere or the solar wind particles don't go past the heliopause. All right. We've been able to take pictures, including my background slide. There's been a few other bow shocks or stellar spheres, astrospheres that we've been able to see around other stars. This one is BZ-CAM up here, and this one it looks like maybe the interstellar wind is moving faster because it looks like the bow shock is a little more peaked. And this one down here is Myra. Is actually a shooting star, a star that is just shooting through the galaxy and creating its own bow shock right here. It's a pretty cool little star. And we also got a little peek at weather balloon activity. I'm going to talk about weather balloons here right now. But you can think of the heliosphere as a weather balloon. Remember how he said that the weather balloon was going to rise and rise and rise until it pops? That's because as a weather balloon rises to higher and higher altitudes, higher and higher altitudes, it expands. So here at launch, you can see the balloon is not filled up all the way. That's because they want to leave room for it to expand as it moves to lower air pressures. So, and that's how most weather balloon journeys end, is the balloon expands and expands and expands, and then it pops and stuff falls back down. But you can think of that as or you can think of the heliosphere as behaving like that. When the heliosphere is inside a high-density environment, or where there's pressure squishing down on the heliosphere will shrink, and when you take it outside of that or put it in a low-density environment, then it'll expand. The purple potato, we're inside the purple potato right now, so it's pushing down on the heliosphere. When we leave the purple potato, or the lick, I could call it the LIC, it will expand. Not very much, because the lick isn't that dense. All right? So the heliosphere is dynamic, and scientists have been able to model what would happen to our heliosphere if we take the density of the local interstellar cloud, that purple potato, and we increase the number of particles in that, like a 1-inch sample box. If we increased it by 50 times, the termination shock, that egg, the innermost boundary of the heliosphere, shrinks from the Kuiper belt, where it is now, outside of Pluto. It shrinks from the Kuiper belt down to Saturn. And that's almost a 90% decrease in the size for just increasing it, the density, 50 times, which is not a big increase in density. So you could imagine finding a cloud that would shrink it even more. So what my advisor and I were looking for in the sun's rearview mirror, we're going this way around the galaxy, we decided to look behind the sun to see if there were any clouds that we might have passed through in our history that were dense enough to compress our heliosphere. And we call that the rearview mirror. I already gave it away. So pardon my animation of a rearview mirror, but this is the best I could do. This is, you can think of it exactly like this. If you're driving along, pretending you're the sun, looking in your rearview mirror, and you see these street lamps and an empty road behind you. Say all of a sudden you see a puff of car exhaust in the background. You can figure out where that car exhaust or that cloud is by looking at which street lamps it blocks out. It should be, I tried to make it clearer, but it's blocking out these three street lamps, but it's not blocking out this one. So you know that the cloud has to be between these two street lamps. And that gives you like an upper and lower limit on the distance to that cloud. Say suddenly a sandstorm sweeps across the road, and you know that this is closer than the car exhaust because it's blocking out all but the 4 closest street lamps. You still with me? Okay. I'm going to say there's one more little dust devil, and you can tell that this one, the dust devil, is closer than the car exhaust because it's blocking out a closer light. So you know it has to be between this one and that one. And I also made this one a funny shape just to illustrate that, you know, clouds are a funny shape and just the same in space. Clouds are going to have holes in them that might try and trick you and make it hard to figure out the distance to, but we've been able to figure it out for the most part. So that's the basis of the analogy. Let's see what it looks like when we go to space. So let's get rid of the road, the ground. And this is the part that counts. And maybe someone could have guessed this, but our stars are the street lamps. Our street lamps are the stars. So we can put those same clouds back in, and the same logic applies. We know that this little space car exhaust has to be between these two stars, and same for a space sandstorm. This is going to be closer than the blue cloud because it's blocking out the same, it's blocking out closer stars. And again, for a space tornado. Yeah. But this isn't what my star field looks like. This is where I was looking. This is the constellation Orion and Eridanus right here. And the direction of the sun's past motion, the center of the road in that rear view mirror, is right there. So now you guys can all go out at night and look next to Rigel and be like, hey, that's where we came from. That's our rear view mirror. And my stars don't look like 2 straight lines going back. They actually look like this. But it's the same deal. The bigger stars are the closer ones. I've made that like that in this diagram to make it easier later. All right. So now I'm going to talk to you about the data and how we're able to find all this stuff. This is McDonald Observatory in Texas that I was lucky enough to go on an observing trip to when I was working on my master's. This was our observing team for the trip. It's me right there. This is my advisor, Seth. This was another student, Marshall, and a postdoc, Adam, who actually got time on the telescope and let me piggyback on the time. And this is me with the telescope that we use. This is me right here. This is the end of the telescope, and now the open end is pointing up there. But this telescope is bigger than Hubble, but, you know, there's an atmosphere in the way, so pictures aren't as clear, but technically bigger. Okay, and now this is a little diagram to show you how we actually collect the data. So this is our little telescope over here on a hill, and say we're looking at a star that's really close to us, maybe the sun. There's nothing really between us and the sun, so we see all the light that's coming from the sun, and that looks like this. So it's just a very simple graph, and this red line, that's 100% of the light. Now if we look at a star that's further away, there might be a cloud between us and that star, and that registers as a little dip in light, because we start with 100% of the light from that star, and then a tiny fraction of it hits that cloud and then gets reflected off in all other directions. So we lose a little bit of the light, and that registers as a little blip or a little dip. in the light. And we could learn a lot from the size, shape, and position of that blip. First thing we can learn is from the line position is how fast the cloud is moving. From the width of the line, we can get the temperature of the cloud. And then from the depth of the line, we can get density. Remember, particles in the box, number of particles in a box. So we can go back here and say we look at one more star that's even further away. Now our light looks like this. There are two blips, and since now you guys are experts in what the size, shape, and depth of this means, this green cloud has got to be warmer and less dense than the blue cloud. It's less dense because it's shorter, and it's wider, so that means it's hotter. So this is how we're able to tell two clouds apart if we're looking at data that looks like this. All right? So now we're going to have a real quick quiz. If this is my raw data, how many clouds do you think I'm looking at? Very good. You guys are so great. So I had some great programs and scripts to kind of help me do this in a very sound way. So this is what my fit to the data looks like, the red line right there. All right, you ready for another one? How many clouds? That's a good guess, right? So we think there's about 10 in here. There could be more, there could be less. We're limited by our telescope and our fitting procedures. But we're pretty confident that there's maybe around 10 in here, and that's what all the different colors are. So me fitting lines, or the red profiles to this data, took me about a summer, and this is about half of all the data. If I put all the data on there, then you wouldn't be able to see anything, and you'd think I was crazy. You might still think I'm crazy. But yeah, I spent an entire summer analyzing this data. And from that, we were able to find a few clouds, or clouds that we think are there. So just a reminder, here are street lamps. Bigger stars are closer stars. And this is kind of a map of our first cloud that we found. Because I'm incredibly creative, I named it Cloud A. So for Cloud A, any star that's dimmed red means that when we looked at that star, we saw a dip that came from the same cloud. And so all of these stars had a dip that looked very similar. So we were able to match these blips together. These stars in front that aren't dimmed red, or they aren't colored red, they're in front of the cloud. So when we looked at those stars, these are like the nearby street lamps, we didn't see any signature of that cloud. Here's a second cloud we found, Cloud B. This one was a little funny shaped. Showed up in that star, but not in the one before it, or in any of these stars. And this is Cloud C. So can you tell which ones it's covering up? Maybe I should have made it darker. But it's, yeah, so these four in front didn't show any green blips, but the ones behind them did. So those are the three clouds. And when you put them all together, because we're able to figure out distances to them, stack them on top, this is what they look like all together. So the green cloud, or Cloud C, turned out to be the closest, and the red cloud was in the middle, and the blue cloud was in the back. All right. So we know the distances to these clouds, we know their velocities, we know their temperatures, and we know their densities. So we can do a bunch of math and figure out what they would have done to our heliosphere when we passed through them, if we passed through them. And this is what that looks like. Now there's a lot going on here. We're going to walk through it. So on the x-axis down here is time in millions of years ago. So we're looking at a history. It goes from 2 to 4 million years ago. On the y-axis, we have distance from the sun. And are you guys familiar with the powers of 10 video, or jumping up in powers of 10? So this is a logarithmic scale, or a powers of 10 scale. So this is 10 astronomical units from the sun. And remember, an astronomical unit is the distance from the Earth to the sun, 93 million miles. So this is 10 times that distance, 100 times, and then 1,000. And here are the outermost planets. We have orbital distance for Saturn, Uranus, and Neptune. And this region right here is the Kuiper belt. These dotted lines up here, those are those three termination shock three heliosphere boundaries that I talked about earlier. The termination shock, the heliopause, and the bow shock. These groupings of lines right here, those are where those three heliosphere boundaries were when we moved through each of those clouds, if we moved through those clouds. So we have cloud A, cloud B, and cloud C. Cloud A and B compress the heliosphere, squish down the heliosphere enough to where the innermost boundary, the termination shock, was almost to Saturn's orbit. Cloud C was not as extreme, but still inside Neptune's orbit. So what this means, remember the solar wind particles stop at the heliopause, that red bar right there. So what this means if the heliosphere passed through these clouds, Uranus, Neptune, and the Kuiper belt would be orbiting the sun, but they'd be in outer space. They wouldn't be feeling the solar wind anymore. The solar wind would be inside of their orbit. All right. We're going to take a little break. Because I know I just threw a lot of information at you. And we're going to review a couple points before we move on. So there's my cloud maps, just for you, because I like looking at them. What I want you to remember, first of all, is the heliosphere is that bubble surrounding our solar system, and it can get bigger or smaller. It's dynamic. I think you guys are pros at that now. Other thing I want you to remember, interstellar medium is a wide range of densities. You can have 8 particles in a box. You can have 200,000 particles in a box. Sometimes you have to take 1,000 boxes before you find one particle. That's how very thin some of this interstellar medium can be. And remember the concept of the sun's rearview mirror. We looked back, we found clouds, and they could have, if we did pass through them, they could have squeezed down our heliosphere. Okay, at this point, a few of you might have a really fair and valid question. Why do we care? And we care because of things called cosmic rays. You guys heard of cosmic rays? I'm sure you have. All right. So you've probably seen this before. This is a map or a drawing of what happens when a cosmic ray hits an atom in our Earth's atmosphere. First, you got to know that cosmic rays are not rays. They're not light. They're high-energy particles that are moving at almost the speed of light. We're pretty sure they're formed in supernovas, and they're coming from everywhere in the universe. We can't find one cosmic ray and identify its origin. They are passing through us right now, but they have been for a millennia. I told my roommate about this. She kind of freaked out. It's not a big deal. It's not scary. It's cosmic rays have been here for as long as we have. It's all right, and even longer. And actually, it's we know pretty well how much radiation we're exposed to from cosmic rays, and it makes up only about 10% of our total radiation exposure from Earth and man-made sources. All right. So this is another model of a cosmic ray shower. This is the original cosmic ray coming in here, hitting an atom in our atmosphere, and exploding. So it hits a particle and shatters into all these other particles, lower energy particles that are still moving really fast, and those particles will go off and create other smaller showers, and that'll happen all the way down to the ground and below. So a lot of particles are created. A lot of electrons are created in a cosmic ray shower. Here's a movie of this happening, or a animation. Okay, so remember, these are moving at 99% of the speed of light, or very, very fast. So this is dramatically slowed down, so you can see it happening. This is the cosmic ray coming in, and you see the original a collision happened up there. But smaller collisions keep happening as you go down. That's Chicago. Sorry if we have any native Chicagoans here. But, yeah. It's kind of cool, huh? Well, pretty. Okay. So these things are happening all the time, but we're actually pretty well protected from cosmic rays. Here's another diagram of that ray shower. We have three shields against cosmic rays. The first one is Earth's atmosphere, and that's what we've been looking at. We've been looking at the cosmic ray shower that happens when a cosmic ray makes it all the way to Earth's atmosphere and shatters. The second shield going out is Earth's magnetic field, because these cosmic rays are charged particles, and charged particles are diverted by magnetic fields. So if it runs into Earth's magnetic field, it'll get diverted and go someplace else. But the first shield we have is our heliosphere, because inside that egg is a strong magnetic field that's put out by the sun, and that will also divert cosmic rays. And maybe a few of you were able to guess this, but if you reduce the size of the heliosphere, you reduce the amount of protection. And I have a video kind of showing that. So termination shock, heliopause, bioshock's not here, sorry. So these things zooming in are supposed to be cosmic rays, and when it gets compressed and this turns red, you can see that more cosmic rays are making it into the innermost boundary. And when it's bigger, less are making it through. So lots of cosmic rays making it in, less cosmic rays making it in. One more time. More, less. And this matters because there's cosmic rays. If you increase the amount of cosmic rays hitting the planet, that's going to have some effect on the planet. So like I said, there's a lot of electrons produced in a cosmic ray shower. One of my roommates said this kind of looked like like an alien space gun or something. Cosmic rays. So a lot of electrons can seed lightning strikes. And that's kind of interesting. There's a possibility that these cosmic ray showers can have an effect on cloud formation. And that matters because if you create more clouds, more sunlight is being reflected off into space. So that could lead to periods of global cooling. Increased mutation rates, because these cosmic rays are hitting us too. And I don't want this to sound like a scary thing. But they cause damages to our cells, and sometimes those get translated as mutations. And I think that's kind of a cool side effect. Like mutant powers, right? And the last one I'm going to talk about is they can alter the atmospheric chemistry. A cosmic ray will come in, they make nitrous oxide or nitrogen oxide, dioxide, one of those, NO and NO2, chemistry. So they'll create those, and those have an effect on life forms, but they also create special isotopes, and isotopes are variations on elements. It's like if you take an element and then remove a neutron. It's a different type of element. But what happens is those isotopes are created in the upper atmosphere, and then they fall down to the Earth's surface and get locked up in ice cores and sediment cores. And sediment cores are coming from the bottom of the ocean. But you slice them open, and you can recreate abundances of these isotopes as a function of time. And then you can make really cool graphs like this. So this is an abundance of one isotope here and another one over here. This one can be directly related to global temperature as a function of time. And this plot, age 0, current time, is up here at the top, and 70 million years ago is down here at the bottom. Some of these wiggles have been identified. Like this sharp one corresponds to a certain glaciation that happened around 35 million years ago. This one's been identified too. But a lot of these gradual changes haven't been identified, and that could be due to our sun's passage through a dense cloud. If you squeeze down the heliosphere, more cosmic rays, that could have an effect on the isotopes that we're recording here. So that's the big idea behind this project. And what I like about that is, I just like this slide, so I'm going to put it up again. What I like about this project is it's astronomy that touches the ground, that touches us. And I know we've all heard Carl Sagan's we're all made of star stuff, and he's talking about the elements that are made in the cores of supernovas or as they're exploding. And without those supernovas, life as we know it wouldn't exist. But those supernovas also made cosmic rays, and those cosmic rays are hitting us and continually changing our planet and maybe even changing us. So a nice time element that I hadn't really been aware of before I worked on this project. So, conclusion, this is where we've looked so far, and we actually have data looking out the sun's windshield. So check back later for a forecast of interstellar medium clouds. And that'll take questions.